Thanks for Kathleen's introduction, and also thanks to you all for being here for my talk. So today, my talk will mainly focus our recent experiment, alpha clustering in heavy nuclei. And also I will introduce a little bit about our future projects in light neutron-rich nuclei at RIBF. So they are both PB-alpha experiments, but considering experimental measurement as they are very different. So finally, I'll come back to a short summary. So when we talk about the nucleus, probably the first image in your mind is like this mean field-like picture. So you have many nucleons moving independently in the same nuclear, let's say, attractive mean field. But at the beginning, we already know that this kind of picture is not complete. So if we do some simple calculation about the nucleon separation in the nucleus, either from the nuclear saturation density or from the universal scaling of the radius, you can know it's like 1.8 Fermi. So this is significantly larger than the nucleon size, is about 0.85 Fermi. So that means it's not very crowded actually in this interior region of the nucleus. So the nucleons, if they like, they can choose to be a pair or form 2 or 3 bodies clusters. So that is what I want to talk today. So then I will start with a simple question: what we should talk about when we talk about the nuclear clusters? So let's start from the simplest case, the 2 nucleon case. So we already know very well there can be 2 types of nucleon pairs in the nuclear system. One is we call BCS-like. So this is very long range. The size of the pair is comparable to the size of the whole nucleus. So another is dineutron. So for this, we are very interested. So in neutron-rich nuclear systems, so we see many talks during this reaction similar. So they can be very compact, maybe 2 Fermi, for example, at the surface of like Lichen 11. And also similar scenarios can also be expected in the nuclear matter, actually. Here is a theoretical calculation by Matsuo. So here's the essence, like the size. If you see the cluster, it should be not very huge as in comparison to the nuclear size. It should be rather compact. So another thing is, so nucleus is the nucleus. In any sense, it's a quantum system. What we have in hand is a wave function. So then, in principle, we should analyze everything based on the wave function. So one may ask, if I find some alpha-like component from the wave function, then do I find alpha cluster there or not? So this is some question I think many people may once. This is under debate. I think for many people. So this is actually already there is an answer maybe 50 or 60 years ago. This is known as Bayman-Born theory. So this is very simple mathematics. You just do some calculation of this oxygen 16 wave function, and then finally you find you can write it in many different forms. They're equivalent. It's equivalent to alpha plus carbon 12 or alpha plus carbon 12 2 plus state. They're equivalent. So this means the wave function itself, there can be anything. So this is we call the duality of the nuclear wave function. So on one hand, it means there can be nuclear clusters there or there cannot be. On the other hand, the wave function itself is not sufficient when we discuss the nuclear clusters. So there should be something above this nuclear wave function only. So on the right-hand side, I show you some. So this is a measurement in heavy inclinations. So they measure the effective binding energy of the clusters. I don't know the detail. Based on some method that determined the binding energy of the clusters with respect to the density of the nuclear medium. And they find, similar to the dineutron case, as a low density region, there can be some, really, some clusters, they have some effective bindings. So they are different from the nuclear matter they are inside. So then this leads us to this very well-known Ikeda diagram for nuclear physics in nuclear cluster communities. So the rule is very simple. So the clusters tend to be developed close to the corresponding cluster decay threshold. So this is just a simple picture. So the relative, in case the state is very close to the cluster threshold, that means the relative energy between the cluster unit is very small as compared to the binding energy of the clusters. So that means the clusters, the binding is very, very strong. You can not easily break it. so they can be well kept. So the well-known example is Hoyle state, and in recent years, people also think about maybe it's also valid this kind of threshold rule for the bineutron cluster case. So here I just put a simple picture here. So so when we discuss the cluster, so this is important for my following discussions. So we discuss the cluster, the inside correlation or interaction should be rather strong. The inside the cluster should be strong, but the interaction of the cluster with the media would be rather weak. So in this sense, then the cluster we can say is well formed. So there soon be the hot summer in China or in Japan. So maybe many people like drink ice water or soda water. So we will see sometimes we see I see a bit of ice inside, or sometimes you see I see a gas bubble inside your water. So that's fine. But maybe it's questionable if you say like I see a drop of water in my water, because that water is no difference with the other water inside your cup. So there should be some difference, or sometimes we see the scale separation or decoupling of this cluster unit with the nuclear environment. So in nuclear systems, in principle, you can have anything. You can have either mean field type, dynamic configurations, or you can have cluster configurations. So what do you observe in your experiment depending on your experiment? So what do you want to observe? Then in principle, you may observe it, and you may skip the other configurations. So in China, I guess all my Chinese colleagues know this ancient point very well. So this actually we learned this in our elementary school. So that means this point says like if we see a mountain, so we may see like ridge, or it's a like peak, or you see like maybe only see the cliff, or you see this other flat only with many trees. So depending on what your viewpoint, you may see the mountain or the different, completely different. So that is the essence of this cluster. So it's not something weird, let's say the cluster. It's already there written in the nuclear function, and it's also already automatically accommodated in the same nuclear mini-body systems. Just maybe sometimes we just ignore it because to explain our experiment observables, we don't need it. But there are some cases we really need this kind of clustering component. So here I show you one example in polonium 212. So this is kind of a textbook example of the alpha decay. It's a very strong alpha source. So many people think it's simply alpha particle on top of lead to its core. So many people think it like this way. So of course, it's not as simple. So now many theories try to reproduce this absolute alpha decay half-life from microscopic theory like shear model, but still it cannot be reached. If you can, even if you consider, for example, like pairing or even continuing effect, anything you cannot. It's very difficult. There is still some gap, like a factor of 3 or 5. It's very to reach this kind of discrepancy. So, but some people can achieve it. But if you just accept the alpha clustering is indeed some essential ingredient in the polonium 212 nucleus, then you can construct a model with both with a mixture of shear model configurations and alpha clustering configurations. So then here you can see on the left side, you can see clearly the alpha clustering component can be nicely reproduced. Here you should be careful about this shear model calculation. So this has been a multiplied factor of 10. So in reality, this will be much smaller. So on the right side, this is the gamma ray measurement. So here they measured many gamma transitions, and interestingly, they observed some non-natural parity states, which you can see here, and they are associated very strong E1 transition. So this cannot be interpreted with the shear model configurations. So what they did is they again consider this kind of combined configuration with both alpha clustering and also shear model. So the shear model configurations nicely interpreted this kind of, let's say, normal B2 transition. On the other hand, this kind of alpha clustering component, they can explain these non-natural spin states and their enhanced event transitions. So recent years, of course, so for nuclear cluster studies, the interest also comes from their impact in implication for astrophysical processes. So the most pronounced example is a Hall state. So for nuclear cluster people, we always do advertisement based on this Hall state. So it's a bit boring, but it works. So people like this kind of statement. This is related to the carbon fusion and also important for human life. So yeah, that's true. So with this Hall state has well-developed 3-alpha cluster structure. This 3-alpha process is largely enhanced. Then the carbon, we have enough carbon for carbon-based life. So without this, maybe we do not have human life. But that does not mean there may not be life. There may be some other form of life, for example, based on iron or silicon. So maybe that's good for some people if you want to have superpower, but I don't know it's good or not. So this actually this kind of enhancement, so it's not unique for Hall state. In any reaction, this kind of astrophysical capture process, if you have some cluster states close to the threshold with well-developed cluster states, the reaction will automatically be enhanced by a factor of 10 or even more. So, and also this clusters will affect the nuclear matter. So this will be covered in my second part of my talk. So in general, you have two ways to find the clusters. If you really want to find the clusters, so one is you go to the excitation. So then, as we'll explain in the Ecta diagram, and close to the corresponding decay ratio, you will find many cluster states. And another way is you go to the neutron-rich site, for example, or proton-rich site should be similar. Then you will find many cluster even in the ground state. So in the excited state of light nuclei, so we have many novel, many interesting cluster structures. You can see molecular states, for example, in Brain 12. So this is actually my PhD thesis work. We've observed very interesting states, and we established kind of standard method to study the cluster structure in the neutron-rich nuclei. And also there are some linear chain states in carbon nuclei, and also some gas-like states. So some people say there may be the alpha condensate. So this really goes beyond the nuclear physics community, has far-reaching impact. So now I already almost changed my research topic. I basically go to the ground state. Today I will talk about, but Peking University, my supervisor still keeps the interest. So now still is this active center for cluster states in nuclear rich nucleus. So this is recently very nice work on carbon-16. So to study the cluster in the ground state, in principle, the best way is PP alpha. You just lock it out. You cannot observe it decay, or it do not come out. The other observables do not work for this alpha cluster in the ground state. So you can either use normal kinematics or inverse kinematics. In case of normal kinematics, what you do is you use the proton beam, and then you put the target here. Then you alpha is knockout. In the detectors, you detect alpha and the proton. Then you can get the cross section, or you check the coincidence. Then in the inverse kinematics case, then you can use the unstable beam. In this case, you have proton target. So then finally you observe, you need this beam information, this locked out cluster and proton. And in principle, you also need this residue, since it will help you to select the reaction channel. That's very helpful for this kind of unstable beam experiment. So here we always use quasi-free. What does this quasi-free mean? So generally we want to go to some higher beam energy. In this case, the reaction. Let's say the reaction time is very short. So the so-called impulse approximation is valid here. So another thing is the transferred momentum or transferred energy should be rather large relative to the binding energy of this alpha cluster. In that case, the residual can be well considered as a spectator. So the alpha cluster is removed kind of freely. We call quasi-free. So then the reaction is much simpler. Of course, you still need some reaction model. You need to consider the distortion effect in the incident and exit channel. So okay, so now I come to the main part of my talk. So this is about our recent experiment, alpha clustering, we performed at RCMP in heavy nuclei. So one of the motivation for this project, of course, is about alpha decay. So now we heard a lot about alpha decay, especially the super allowed alpha decay, and also this super heavy elements. Now very popular in Japan is Nihonrin. So actually what we know about alpha decay since maybe 100 years ago of Gamo's years is still this. Now, of course, we have many nice theoretical progress, but still basically the picture is the same. It's like we assume there is an alpha particle, then it goes through this Coulomb barrier through some quantum tunneling process. So, okay, so here I show you a figure, a simple cartoon about this this alpha decay problem. So in principle, here are two ingredients in this Gamo model. So first we assume alpha cluster, then there is a tunneling of this alpha cluster. So, but finally, in observation, we have only one observable half-life. So many theories, they basically handle the two together. So that means these two kind of combine into a black box. Finally, what comes out is a half-life. So as I talked before, like there's still a challenge that the theory, they cannot, I mean, the microscopic certain calculation still is out of the, I mean, it's still difficult for them to reproduce absolute alpha decay half-life. So yeah, so I would say the assumption, let's say the Gamma model is not a bad one, although we based on kind of a two assumption because it works. In nuclear physics, we have many assumption approximations. But from point of view of the research, I think we still need some measurement independent of the alpha decay process to really to probe this alpha clustering process. In this way, we can really provide so direct evidence for this alpha clustering. So still we need to keep in mind, so alpha clustering, alpha decay is not proved. It's a kind of postulated in the alpha decay model of Gamow. Yeah, so that's one of the motivation. So another motivation comes from this nuclear equation of state studies. So here I guess you know well. So this nuclear equation of state, you can expand it, then you will get some parameters. So it's a symmetry energy, then you can expand it again. So then you will get this J and L parameter, and also this, for example, here is a key parameter. So this is very important in nuclear physics. So now we have many experiments, many projects to go targeting at these parameters. So here on the left side, I show you some current data. You can see we have many different experiments trying to constrain these parameters. So why the neutral skin matters is, so here, if in principle, we don't know where it is. So what we do is we can do different certain calculations depending on different effective interactions. Then you can see this linear correlation between this L parameter and the neutral skin. So in experiment, you will get this neutral skin, and then with this linear relationship, you can know where this L parameter is. So then alpha clustering comes into effect. So the idea is, so one of our theory colleagues, he's also one of the principal investigator of this project. So he made the relativistic density functional calculation, including both the nuclei and light clusters in the nuclear matter. So he found indeed in the there is a window, low density window, the light clusters can be developed. So this is consistent with, I already showed you this heavy ion measurements at the low density region, the light clusters can be developed. So this will affect the nuclear equation of state. So let's come to the more practical discussion. So then let's come to the, as I said, how we determine this some nuclear equation of state parameters. So one is from the neutral skin. the alpha clustering, when you have the alpha clustering in the surface of the the heavy nuclei, so that is also low density region, right? So it can also be developed in principle alpha clustering. So if alpha cluster form, then it will affect the properties of the surface of heavy nuclei. So what is the effect? The effect is it will suppress the neutral skin. So that means, so in reality, if this theory is right, in reality, the neutral skin you expect it maybe too high. In reality, it's smaller because alpha clustering is there, but you ignore it in your model. So kind of you overestimate the neutral skin. So this is very important. So we have to go to it. So yeah, because one important constraint of the nuclear equation of state comes from the neutral skin thickness. So this is some good prediction, but it sounds like it's impossible to prove it because we have only one late to 8, for example. We have only one neutral skin thickness. It's there. We measure it. It's there. How we can know it's like from alpha clustering effect or from the nuclear the effective interaction? Because to match the predicted neutral skin thickness, you have to choose. One is to change a model, for example, consider alpha clustering. Another way is you change your effective interaction, right? You have two choices. Here it seems we have no way because we have only one late to 8. We don't have anything like CRISPR for gene editing. We cannot say we throw in any alpha clusters and see how the neutral skin will be affected. But actually, there is some ways. So we can check the other side of the coin. So since the alpha clustering will suppress the neutral skin, so that means the neutral skin will also suppress alpha clustering if alpha clustering rarely occur in the surface of heavy nuclei. So then as you have more and more neutral skin developed, then the alpha clustering will suppress. So this gives us the opportunity to go to experimental is a justification of this theoretical prediction. So then my theoretical colleague say, you can go to lay and tin isotopes. That's a good system. So I predict there can be alpha clustering there on the surface of tin nuclei. So tin we have the magic number, proton magic number z equal 50. So I don't know, many people say it's impossible. You cannot find alpha cluster there. So it's impossible, some people say. But my theory, the theorist Tibel say, you should go, there are alpha clusters there. And if you go, you'll see that it decreases when you go to the neutron rich side because of the development of the neutral skin. So yeah, then we just say, okay, let's go. So then we decided to go to the direct measurement of this. Of course, we don't need to go to all the isotopes. We just pick up 4, T112, 116, and 20 and 24. I just see how this systematics goes. So here I want to mention one important ingredient of our advantage of our measurement is we only check the systematics. So the absolute value has many problems. One is model dependent, and another is a definition, how you define this absolute value. This is still not clear, I think. For example, the spectroscopic factor, even for single particle case, the definition is not very clear. So, but in our case, we go to the systematics. So let's say the relative value. So it decrease or not decrease, or you increase. So that is basically we can say it's model independent. So our experiment was performed at RCMP. So here is the layout. So okay, I only say this part. Here we have this beam, proton beam, and then the experiment was measured here, performed here. So we have two high resolution spectroscopic here. So how high resolution here? I can give you an example. So this is alpha in hexagon. You can see the resolution is like 20 keV. So it's very high resolution. Actually, it's too good at our experiment. So this is theta boron target. It seems the measurement is very simple. We put target there, then we send in the proton beam, and then we look at alpha. After the experiment, we measure alpha and measure proton. So and these spectrometers are already constructed there for maybe 10 or 20 years. It seems the experiment is very simple. So actually it's not so simple because this is kind of a stable beam experiment. The beam intensity is very high, and later you will see our reaction cross section is like in order of nano bar. Basically, we're talking about the cross section like 100 millibar, or maybe to the extreme case 1 millibar. But here the cross section is only nanobar. So that means we need to be very careful about the random coincidence and also the signal. And also this spectrometer are basically designed for high energy particles, not for low energy alpha particles. Here we have only like 50 MeV. It seems not so low, but it's low for this spectrometer. So we did a lot of work to improve the detector system. So here, I just show you one example. So we did we worked on this maybe 3 years. Not every day, but we worked a lot. So on the right side, you can see this is when we started the project. This is spectrum we have. So you can see maybe we see some alpha here, and then we see a lot of contamination, but from other maybe Z-equal particles. But after we optimize the setup, on the left side, you can see that we almost see only alpha particle, kind of background-free measurement. So at first we go to kind of prove a principal measurement with lesion target. So this is the simplest case. Of course, lesion 7 we can simply consider is alpha plus 1 triton. So it's a very simple structure. So what we do is in experiment we have proton, we have alpha, then we check the coincidence. We don't have many signals actually in this kind of experiment. This is a timing difference of proton and alpha. So you can see the real coincidence peak, and then of course at the same time you will see some random coincidence peak. And then if we check the momentum correlation, you can see for the real coincidence, this linear correlation is very nice. And also if you check the accident coincidence, you will see some smeared random distribution of these events. And then we can also, with this, we have the proton and alpha energy. So we can, from energy conservation, we can reconstruct the alpha separation energy. So this will give a definite proof if we really observed this alpha or not. So here you can see clearly this peak. So the lesion 7 alpha separation energy about 2.5. I think this is exactly there. And also you will see very low accidental coincidence in the lesion 7 case. So this clearly demonstrates that now we are ready to go to real physics measurement. So this is then we use I show you some result with tin target. This is a physical result. So here the first step for us is to confirm the coincidence between proton and alpha. So since we just changed the target, so this correlation pattern will not change. So if on the left side, on the lesion 7 case, the real coincidence is here, maybe on the 3rd peak, then in the physics measurement, it should still be there. So here, then we can see, indeed, we can see enhancement there, but here, the random coincidence relatively is much higher. So that, as I say, the cross-section now in tin case is too small, only nanobar. Yeah, but we indeed see this correlation. And then we can reconstruct this missing mass spectrum. So the black points are the real data, the real coincidence, not the real coincidence, and the spectrum within the real coincidence window. Of course, it has both the real coincidence events and also the random coincidence event. The random coincidence is always there. We have no way to remove it from the electronics. And this blue we constructed from the accidental coincidence. So you can see the clearly enhancement. There is a peak, and then you can subtract this random coincidence from the spectrum. Then we can see this nice spectrum. So we see a peak at about 1.9 MeV. So this agrees nicely with alpha separation energy of tin 112. So, and also we have a good resolution here. So as I said, the resolution of the spectrometer is like 20 kV, but it's impossible for us to achieve that resolution because we need to put 6 targets there. Otherwise, we do not have enough statistics. So this is kind of a compromise. So here I show you the spectrum or missing mass spectrum for all the physical targets. So tin 112, 126, 120, and 124. For each case, we see clearly the expected peak, so which correspond to the knockout of alpha from the surface. So the residual is almost, let's say, decoupled in the ground state. So we can see clearly this peak. So for each peak, it agrees with alpha separation energy. So this already provide direct strong evidence that alpha cluster indeed formed as a surface of this tin isotope. So also one thing I want to mention is that in our experiment, the detector, not the actual spectrometer, so they have very limited acceptance. So we set they are both the geometric, the angle, and also the momentum acceptance according to the quasi-free lockout of alpha. So that means already the detector setting limit that if you observe P alpha coincidence already this already point to the knockout of preformed alpha particle. Yeah. So of course we can go a bit more. So we are more interested about the systematics. So here we already have the cross section for each reaction. So then we can, as I said, if we really want to discuss some structure ingredient, you need to consider the distortion effect. So in our case, so here I show you that the black points are the cross section of our experiment result. And also we have some reaction theory calculation. So in this calculation, we input the alpha cluster wave function from theory calculation. And then we also consider the distortion effect in the incident and excident channel. Yeah. So then in principle, if, I can not say the absolute value because that, as I said, it can be model dependent, but the systematics we can see clearly. This kind of decrease from T112 to T124 is nicely reproduced. So we can put this figure in a different way. They're actually equivalent because this cross section, the ratio, give you kind of a spectroscopic factor like quantity. So you can normalize the theoretical predicted alpha clustering strength by this cross-section ratio. Then you can determine the experimental alpha clustering strength. This has some meaning of the spectroscopic factor. So you can see again, this is more clear. So you can see clearly that the decrease as predicted by this calculation, the decrease from T112 to T124 by about a factor of 2. So this is really from the structure. There are really alpha cluster and they get suppressed because of the development of the neutral skin thickness. So this, as I said at the beginning, so our results, well, they provide direct evidence that the development of neutral skin will suppress alpha clustering. Then automatically, it comes to the conclusion that the alpha clustering will also lead to suppression of the neutral skin thickness. So this effect will have implication for our understanding of the nuclear equation of state. So then if we come back again to let's check the neutral skin, really check the neutral skin thickness. So this is what actually we didn't do this before our experiment results. So after we get this experimental results, so we come back to check this one. Yeah. So here I just put some experimental results I got from the literature. So these data points, and then the gray dotted line is the standard mean-field calculation. So without the alpha clustering effect. So if you don't know this blue line, you can also say it's consistent, right? The systematics. But then we considered this alpha clustering effect in this mean-field calculation. Then you can see here this line get let's say the alpha clustering will suppress the neutral skin thickness for all the cases. So then the blue line agrees much better than this gray dotted line. So in particular, if you check this red triangle, this is from the proton scattering. Generally, we think this is less model dependent to determine neutral skin thickness. So here you can see the agreement, especially for this proton scattering results, the agreement is very good. So these are the collaboration. So we have many collaborators from many institutions and many countries. So here I and Professor Tam Oman, the spokesperson of this project. And this is Dr. I don't know if you can see my mouse. The first row, this is Dr. Jungi Talaga. He made the main part of the data analysis. Yeah. So, and we also have this big contribution from Peking University in China. They have students working hard for a long time here. Yeah, also I thank the work or the collaborators of this work. So, and of course, we don't want to stop here. So we want to continue this kind of project. So one natural continuation is, of course, the alpha decay. So in the, let me remind you again. So still, of course, we want to go to here. Then automatically, we hope we can, since we have half-life, we have this part, then automatically we can get information if it's really as simple as gamma model assumed, just the penetration, or maybe more complicated. Then we can really go to check if this work, this simple quantum tunneling of alpha particle is as simple as it is. Yeah. So so the first thing we want to check is if we go to the, so since in our first experiment with tin isotopes, actually we say heavy nuclei, actually they are heavy nuclei. So here no alpha particles can be emitted, alpha particles are bound. So there are no alpha emitters, but the alpha decay case is in the other side. So we want to go to this side and see how about, we know there should be alpha clusters there, but we are experimentalists, we should really go there and see they are there or not. So we don't know how it will happen if we go to this region. So you can imagine, according to some simple expectation, for example, you can think maybe it's continuous with alpha bound region, or you may expect some enhancement close to the threshold, according to the Ikeda rule, or you may expect some other things. Anyway, we don't know, so we need to go there. So we want, so in this next we want to go to Neoden, so it covers this region. So we have Neoden 144. So in some sense, it's also alpha source, although the half-life is like 10 to maybe 10 to 14 years. So yeah. So another thing is, I mean, next we want to go to check the deformation effect alpha clustering. So this is some, I just quickly show you like as an introduction. So if you check the systematics of the alpha decay, so then you will see like here I put the sorin. So if you do the fitting with deformed isotope with the Giga-Nato law, then you extrapolate your systematics to the least deformed region. You'll find your line gradually deviate from this experimental half-life. So that means the deformation seems to decrease half-life or boost the alpha decay process. But there are two ingredients, alpha clustering or penetration. So we don't know which are more affected. So yeah, so that's the motivation. So we want to go to simmering. So gradually we can see this deformation, and with the Neoden measurement, we know the alpha binding energy effect. So we combine with Neoden and simmering, so we hope we can also see the deformation effect here. Yeah. So well, I already used a lot of time, so I simply introduce our future. Maybe one thing I should say is, so this two measurements are already approved at RCMP. Basically, we are ready for the measurement since we already developed the setup, but now RCMP is shut down for upgrading, so we have to wait. Maybe next year we can have the measurement. Yeah. So now we also have projects with unstable being at RIBF. So one experiment is to go to neutron-rich carbon isotopes. So yeah, so this of course we want to, the physics is we want to understand what would be the driving force behind this alpha clustering. So we can think of this as a simple question. So how will nuclear clustering will be affected by adding neutrons? So along the carbon isotopic chain, when you have more and more excess neutrons, how will alpha clustering be affected? So this simple question actually not so simple for this series. They predict very different scenarios. Here I show you four. So one is the simplest one, the alpha binding energy case. This is yellow line. And another say is a pairing gap. So some people say in heavy nuclei, they check the systematics of the alpha decay above late 2.8. And their conclusion is maybe alpha decay is correlated with the neutron pairing gap. So if we expect a similar thing here, the systematics will be like this black dashed line. And then there are also some other AB initial calculations. This one is a lattice Monte Carlo. So I did some translation of their result. So then they predicted the systematics is similar to the pairing gap. So you can see that may be understandable. Maybe finally they come back to the shear mode framework, probably the effective interactions. So this is the green line. This is AMD calculation. So you can see they are very, very different. So that means there is something to still there is something to do to really get understand the alpha clustering. Yeah, but I think is for light nuclei or heavy nuclei, I believe is basically the picture finally I think they should merge. Now we are running independent, but I think finally to get complete understanding of alpha clustering phenomena, I think finally they will merge at some point. Yeah, so the measurement will be at RIBA based on the summarized spectrometer. So this is a big RIPS B9. So our measurement will be here or about the with the summarized spectrometer. So I will show you the reaction. So here we have unstable carbon beam. Then we have a solid hydrogen target. So after the reaction, we have proton and alpha. So we measure alpha with a telescope. And with proton, we have a high resolution recoil proton spectrometer. So the resolution is very good. So for this kind of experiments, it's very helpful if we have the fragments. So here we put summarize here. So then we can largely reduce the background. So we have a cleaner spectrum. So resolution will be like 1 MeV. So in light nuclei, the good thing is we can have good theoretical support. For heavy nuclei, still it's very difficult to get alpha cluster wave function. But in light nuclei, we have many theories. So like AMD or maybe STHSR models based on several alpha and several neutrons. And AMD, of course, they start from kind of AB initial type. They do not pre-assume the formation of a cluster, but finally they can handle both the alpha cluster and also single nucleon configuration in the same system. So then experiment and in theory can go kind of in parallel. Finally, you can come to the same observable, the triple differential cross-section. With this, we can reliably deduce cluster configurations. Maybe not only one, like for example, alpha plus carbon 12 ground state or alpha plus carbon 12 2+, or many this kind of configurations can be determined in our experiment. So these are the collaborators. So finally, I came to a short summary. So we made the direct measurement of a clustering in heavy nuclei at RCMP. So we established a good experimental setup and technique, which works well for the PP-alpha experiment. And in our first experiment, we obtained clear evidence of alpha cluster formation on the surface of heavy nuclei. And also the interesting point is observed the monotonic decrease of alpha clustering along this isotopic chain. So this imply a tight interplay between the neutron skin alpha clustering. So this has some implications for the nuclear equation of state. And also I introduced a little bit about our future experiment at our RIBF based with neutron-rich carbon isotopes. So this experiment also approved, but we don't know when we can get them in time. We are on the waiting list. So okay, with that, I thank you all for being here for my talk. So yeah, and if any of you have interest for any of these projects I presented, feel free to contact me, and I welcome you to join the collaboration. Thank you.